Iqaluit, or Frobisher Bay as it used to be known, on the southern end of Baffin Island. It's the largest town in the Eastern Arctic, and in fact is the second largest town in all of the Canadian Arctic, second only to the capital of the NWT, which is Yellowknife.
How many people would that be?
I think you're talking about 2,000 to 3,000 people, which isn't a very large place by southern standards, but in the north, typically communities are in the 400 person range. It's mainly a government centre and communication centre at the present time. Essentially we fly either along or alongside Baffin Island. We cross Lancaster Sound, which is the Northwest Passage, and we go into the northern part of the Arctic Islands to Cornwallis Island, and that is where Resolute Bay is. A lot of these shots are sea ice. You can see that even at this time, which is sort of April, early May, the sea is not completely frozen because of course there are tides and currents and things like that, but basically it's still winter, even though already it's 24 hours daylight. And there are shots of the interior of the aircraft as we're going up. And this is a regular jet flight into Resolute. There is one from the east and one from the west, I believe, every week. In the interior here, you can see some of our group. We land in Resolute Bay, and this is the communications and logistical centre of the Northern Arctic Islands. A bit like a military base, except there are no military people there. There are hangars for helicopters, hangars for aircraft. Nearby is the village of Resolute, which is an Inuit village on Lancaster Sound. But the main feature for us is the fact that it's this communication centre. Once each year, a group of icebreakers get in there and resupply this base. The rest of the time it depends on aircraft like ours, and they come in from the east, Montreal largely, and from the west, from Edmonton. And it is the headquarters of the Polar Continental Shelf Project, which is a long title for the organization which in fact provides the aircraft and the radios and the snowmobiles for people working in the very high Arctic. We ship goods there, or we leave them there when we come out each year, and they're locked in various cubicles, and the Polar Continental Shelf saves them for us. We come up, pick them up, load our aircraft, and they fly us out to a base camp. And then you see the Twin Otters. These are de Havilland Twin Otters. They're made in Canada. They are flown all over the world. They're a wonderful bush aircraft and flown by Canadian pilots all over the world. In Antarctica, for example, the one we're looking at in one of these shots actually was in Antarctica the previous winter. That's our winter, but the Antarctic summer. So the same with the helicopters. The helicopters come from British Columbia. And then you see the front-end loader loading our Twin Otter. We have, as it were, chartered this Twin Otter, and it's a 3 or 4 hour flight from here due north to our base camp on Axel Heiberg Island. You see the front-end loader coming, and it has our supplies. Some of those we left there the previous summer, and they've been in store for us. When it's full, it takes off and flies this 3 or 4 hours to Axel Heiberg. And you see our people wandering around. Mike English from Wilfrid Laurier, who was a Trent student, who's now a professor at Wilfrid Laurier, works in the north, and Alex, one of his students, Miles Ecclestone, and myself, which was the group that was going in at this particular time.
And here we go.
Hey guys.
Hi Miles. Here we are in Resolute Bay, taking off for the North Pole. airstrip is a big gravel airstrip, and you get some shots of the base and the town, not the Inuit village, but the town itself, where there are, as I said, it looks like a military base. In fact, in Canada we don't operate them as military bases, but the weather station, for example, is there. The ionospheric research establishment is there. There's a nursing station there, and things like that. And as the plane is taking off, you see those. And Cornwallis Island is a very flat island. It's and you get a sense of that as this aircraft is taking off. It's like a flat desert. In the front is Mike English, he went to Adam Scott Collegiate in Peterborough, then did his PhD and is now a professor working in the north, and myself inside the Twin Otter. And you see all our equipment. It's been brought from Trent to go in with us, and we have to take in everything. In this case we were going only for about a month, but you still have to take everything. It's not easy to get water there, for example. You certainly don't have, there are no trees, so you have to take a good deal of fuel and that kind of thing. The pilot and the co-pilot are fully qualified. They are among the most experienced flyers in the world. And when they leave Resolute, which goodness knows is hundreds if not thousands of miles from anywhere in itself, they're completely on their own. They land on lakes, they land on glaciers, they land on the sea ice. At this season of the year they're mainly on skis, but they've got skis and wheels. Now the interesting thing after this is that Axel Heiberg Island, where we're going, like some of the other islands in the north, is very mountainous. So you go from this flat island where you can see the little shadow of the aircraft on the snow and so on. And then, and by the way, one of the things about the snow up here is that this is truly a desert. At the most you would get 30 centimeters of snow, which would be very little here in Peterborough. And so almost always you can see rocks and so on through it. And so it was still between Cornwallis Island and Axel Heiberg, but there are some good sea ice shots. And the open areas are there, not because the sea ice has melted, but because presumably there's a current or something like that, which keeps stirring the sea ice even all winter long. And that will soon freeze over, and then it'll be solid again, and it'll open up somewhere else. One of the difficulties of travelling away from the shore on sea ice for the Inuit or for the explorers was in fact that, but the sea ice is in fact constantly moving. As we get to Axel Heiberg Island, it gets more and more mountainous essentially, and you start seeing mountains and rocks and so on. And the thing about these mountains is they're not like the Canadian Shield, they're old mountains. They're mountains which are just like the Rockies. In fact, geologically they're exactly the same as the Rockies. The difference is that there are no trees here at all, and so you don't get a perspective. But you see layers of sandstone, layers of basalt, layers of limestone, layers of coal, and all that kind of thing. And in mountains of this type, you get oil. And in fact, oil runs from the Rockies in Alberta through the Mackenzie Delta, all the way through the Arctic, right up to this area where we are now. And there are oil resources under these mountains that we see here. Of course, they're very remote and would be very expensive to develop. As we come in closer to our expedition Fiord, which is the location on western Axel Heiberg where we work, you see land and then you see sea ice, and dotted in the sea ice are icebergs, which all icebergs come from glaciers. So it's a sign we've come to a part of the world where glaciers are flowing down from the mountains and are reaching the sea and are carving off into the sea. And these ones, the icebergs that we see here, have been produced by some glacier, and they've been trapped in the sea ice. And when the sea ice breaks, those icebergs will start moving again. Also, as we're getting to Axel Heiberg, as well as mountains, we start seeing glaciers. And there are no glaciers on Cornwallis Island, where Resolute Bay is, but the region where we're going, there are lots of glaciers, and one of the reasons we're going there is in fact to study them. So in some of these shots you see glaciers with crevasses in, and these some of these glaciers are hundreds of kilometers long and perhaps 10 kilometers wide, huge rivers of ice, and they might well be 500 meters thick. So it's a phenomenal amount of ice which is flowing down to the sea, ultimately to produce icebergs. When we get to Axel Heiberg, there is a a triangle-shaped glacier, very clearly shown, and that is the baby glacier, which is one of the glaciers we work on. And we flew in past that, and you could see this triangle very clearly, and then we proceed towards Culler Lake, which is the lake on which our base camp is located.
Welcome to Axel Heiberg, Dr. Adams. Michael?
I didn't have to worry about snow, but...
Oh, that's nice, eh?
Yeah.
What do you think of that?
Not too bad at all.
You see us unloading the aircraft, and again, it gives you an idea. We're only there for a month, but just how much stuff, scientific equipment, food, and emergency equipment, radios, for example, that we have to bring.
Here's some of the old drums that have been here since the 1960s. We've been shipping them out for the last 10 or 15 years, down to a few dozen.
And some groups before us did not take theirs out. The difficulty with oil drums is that they take up the same amount of space empty as they do when they're full. Now we have chiseled the top off quite a few drums, and we fill those up with garbage so we can ship it out, but it nevertheless takes a lot of time and energy to get the drums out, but we have to get them out.
May the 5th, and we're on our way over there, the White Glacier. Peter Adams and myself are going in by a skidoo. Turn around, wave, Pete. And as you see, just in case the skidoo...
You get really close to the skis and the ice accident.
No problem, Pete. This has a zoom lens.
Yeah.
As you can see, just in case the skidoo breaks down, we have to be prepared to ski back down the glacier, which is 13 kilometers long.
And our purpose that day, the White Glacier is one of the glaciers that we are studying. And each year we do a number of things, but one of them is we measure whether the glacier has got thinner or thicker in the previous year. In warm years, of course, the glacier gets thinner, and if that goes on for a number of years, the glacier will actually shrink. In cold years, the glacier gets thicker. More snow is gained than is melted during the summer. And that's a quick way of telling whether the climate is getting warmer or getting colder. And it's interesting to note that in the last 10 years, the glaciers that we work on have all shrunk considerably, which confirms the fact the globe's climate is getting warmer at the present time, perhaps because of the greenhouse effect. Our glaciers are a part of a network around the globe which are used for this quick monitoring of global change.
We're back at base camp after a futile attempt to go up the snow at the skidoo. Only about 3 to 5 centimeters of snow on the snout, and just no grabbing. It just kept sliding down the ice.
Mike English and Alex measuring some snow, and they are doing a survey of snow, and they're looking at how much snow there is there, so we'll know how much will go into the lake when it melts, which it will towards the end of the summer, and then they actually do some chemical measurements with it. But one of the interesting shots is when Alex, I think it is, holds out a piece of snow which he has in his hand, which looks almost like a cube. It looks like a cube of cheese or something like that. And that gives you an idea just how hard the snow is. That's the sort of snow that the Inuit would build igloos out of. And it is formed because the snow there is very thin and very, very cold. There's a fair amount of wildlife in the Arctic Islands, but you don't see it because the animals have to move tremendous distances to get enough food. These two caribou, which you can see are already losing their completely white coat, are called Peary's caribou. They're a bit different from the caribou you see in great big herds because, of course, they can't migrate off the islands. So for many generations they've been living on the islands and have become a bit different from the caribou that appear in hundreds of thousands on the mainland 1,000 or more kilometers away.
We did not make it onto the White Glacier, which you see here, so we did the next best thing, panning away from the Thompson. We decided we'd travel down along with the foxes and the caribou and my shadow to the Sulphur Springs, going into Expedition Valley. Dr. Adams is going out for scale. If you listen very carefully, you can hear it burble.
You see a stream, which by the way is very, very cold. The temperature might be -15 in the water. It's so salty. You can see mud, and then behind it there's a little mound of ice and then layers of ice. And that water is so salty that it flows all winter, and the temperature, it's dark there for 4 months. In the middle of the winter the temperature would be -50. It still flows, and it produces great mounds of ice. We think that this water actually comes from our lake. It comes through a chemically very complicated outcrop, takes on all this salt, and then the mound you see behind the little stream is the mound of ice which is produced during the winter, because the top layer of that water will freeze, and then even though the rest of it keeps flowing, and that forms these mounds of ice. And those mounds spread out perhaps for 800 meters around that location. And if we could see them without the snow, they would be like a pyramid of ice. So they're quite interesting. We measure them because they are one way for us to measure the quite large river which flows in that valley in August each year. And you can use this salt solution to measure the discharge of that stream.
XMH-26, Expedition Fiord, receiving you 5x5, Jim, over.
Clear, go ahead.
Sky condition 15,000 didn't scattered. Visibility 15 plus.
Every day we have to report in for safety reasons. And there's a network, a safety network, that we can radio to from our field radios and from our base camp.
Wind 02 at 2 knots. Altimeter 024. Clouds, altistratus 5.
It's May the 7th. It's a beautiful day. Bit of a northeast wind, as you can see. After yesterday's low cloud, it's a beautiful morning. See who's up. Oh, we're looking at over the part of the Met station, the Stevenson screen and the anemometer. The upper house sleeps 8 in a workshop scientific area on the far side. There's Wolf Mountain panning into view, and I'm out here for a reason, and that reason is over here. Change the far sunshine chart. With 24-hour daylight, you need 2 Campbell-Stoke bright sunshine recorders mounted back to back to track the 24-hour sun.
There's a sign there that says Diplomatic Corps, and it in fact leads to our toilet. And this sequence is going to the toilet with the best view in the world. You go from our sleeping house about 100 meters round a path on a small cliff. Miles shows this sequence here, and then you finally come to 2 drums, and you will notice there the drums, one of them is being used, the others are sealed up. You realize the ground is frozen to 600 meters depth there, so it's not possible even with dynamite to bury sewage, and so we have to seal it up and ultimately ship it out. But from that toilet you get the view of the glacier snouts, the White Glacier that we work on, and then the much larger Thompson Glacier with the pile of rubble in front of it that it's pushed up. Now that glacier, the cliff in front of it, is 60 meters high, and the glacier is 150 kilometers long, which anywhere else in the world, it makes the Athabasca Glacier, which many people have seen in the Rockies, the Athabasca Glacier would just disappear.
There's the group getting ready to go up. Dr. Am's packing up the skidoo. Explaining to Mike and Alex our plans for the day, and I saw them pointing up to our right here, up to the west. I suspect they're looking at the route to Baby Glacier, which lies up that ridge to about there. In the top right hand corner you can see peak of Wolf Mountain, and we cut laterally south and come to the baby glacier after about a 3-hour walk. We made it up onto the White Glacier again. Quite a battle today, but it's a beautiful day. You can see Dr. Adams back there for scale. In the distance, Bastion Ridge, a little Matterhorn, and we'll just pan across the snout of the White Glacier, pick up a bit of the Thompson Moraine before we start getting into too much sunlight.
See how deep the crevasses are on the glacier, and you have to go around those things. On a snowmobile, it's like on the lakes near Peterborough, you're relatively safe as long as the snowmobile is moving, because its weight per square centimeter is not very great. But if you step off the snowmobile, you quite often are you might find yourself on a bridge of snow and you would go through it because your weight per square centimeter is greater. So there's a sequence with the crevasses in the background, and then one of us on skis trying to see, we have to do some work in this area, trying to see if in fact there are crevasses there so we can get past them to do some work. You'll notice that we are roped together, and if the snowmobile were nearer, we would probably be roped to the snowmobile because there are only two of us, and it's not easy for one person to get another out of a crevasse. It's much better if you have three, but in fact there were only two of us working on the glacier at this particular time. The crevasses in the background are about 2 kilometers away, which gives you some idea how clear the air is there. On this glacier we have points marked by aluminum poles, either drilled in the ice or buried in the snow, depending where we are on the glacier. On a glacier, what you have to do to get an idea if it's shrinking or growing is you have to measure how much snow came in during the winter, and then you have to measure how much melting went on in the following summer. And if more snow came in than melted, then the glacier of course is bigger. If there's more melting than accumulation of snow, then of course the glacier is smaller. So at the top of the glacier, which is where this sequence is, all you've got is snow. And in fact, if you dug down, if you dug a tunnel 100 meters down, you would largely be in snow, because the snow accumulates and accumulates, and then gradually, when it gets to be buried at a great depth, it turns into ice, and that flows down and becomes the glacier. So at the top here, we are measuring, first of all, the depth of snow which fell that winter, and then secondly, with these instruments, we're trying to measure, for example, how much water that snow represents. We also look at the crystals of the snow, because we have to pick out where the winter began, and you realize this snow simply fell on the previous year's snow. We're very high up and it doesn't melt very much. So this sequence shows us measuring the accumulation of snow on the glacier, which is one half of the equation, the other half being melt, which gives us the information whether the glacier is getting bigger or smaller. Miles Ecclestone and I have worked for many years on glaciers. We've also worked on the Kawartha Lakes in winter, measuring the ice and the effect of the ice on the fish and things like that. And we've also worked in Labrador on lakes. So he and I have done a fair amount of snow and ice work together. You get some idea of how much snow there is here from the hole that we've dug. The hole, by the way, is deeper than 1 year's snowfall, but that is the total snow which fell in this area that winter. Here we've got a surface layer, goes down to there, and that's really, really hard. Look, you can't even poke it with your finger, okay? And then you've got another layer which is softer but is reasonably hard, and it goes down to about there, okay? So that's 2 layers. And then below that, right here, we have this very, very loose material. And so what we do is we sample each of those layers, and first of all we do it for density. So to do density, we take a volume, for example, of this layer here, like this. When it's flush like that, we lift it out, like so. Put the lid on, like so. And then we take a scale, which is just really an angler's scale, and we weigh it, and then we have the weight of a known volume, which is the density. The lowest layer that we can see in here, this very loose layer, is what's called depth hoar. It's built up while there's a temperature gradient in the snow, and it consists of very large, very weak crystals. And in avalanche areas, this is one. In avalanche areas, that's one of the causes of avalanches. The underlying layer of the snow becomes very weak with this depth hoar, and away it goes. Okay. To look at the crystal size, we have a thing like this. We take a few of the crystals, like that, there, and we simply take a hand lens, which is the one I have here. We look at it like this, and there's gradations of 1 millimeter in there, and we determine the type. For example, this is depth hoar. Probably 4 millimeters would be the largest one that we would see. And then, typically at this point, we stop. We take our, you'll notice this, what? No garbage. It's Quaker oat granola bar, and we eat it. And this particular one isn't as soft and crunchy as they usually are because it froze solid while we were waiting to film it. As we're coming down the glacier, you'll see some shots of one of our safety locations on the side of the glacier. This is a moraine where there are some rocks. You can come off the ice, and each year in the metal box you see, which protects it against animals, we leave some basic equipment, and we also leave an old tent there and some other things for safety reasons. Now, some years we would stay at this location for several days while we work in the higher part of the glacier to save us going all the way down. Some years we would simply, as we in this occasion, be there for one day. The fact that it's 24 hours daylight means that we can work for 20 hours, for example. One of these shots shows us finding a cable in the glacier, and we use those cables also for measuring the amount of snow and the amount of melting. The cables were inserted many years ago, well, let's say 10 years ago, by drilling with hot water to the bottom of the glacier, and they were used for measuring the temperature of the glacier, which allows you to calculate how quickly it's flowing. And they're very useful to us now because, unlike our stakes, every year our stakes, they get buried and we lose them, or so much melting goes on that they melt out. But these cables, as long as we can find them, are a very good way of, quick way of measuring the thickness of snow, or, as I say, the amount of ice which is melted. After the long sequence in which we're coming down the glacier and it's all bouncing around, there's a shot at the tongue of the glacier, which gives you an idea of what it's like at the very end. This is as far as it got before it melted. And you can see there are icicles hanging off it because melting occurred there the previous summer, and then embedded in the ice there are all the boulders and so on that it picked up. The entire Peterborough area, all the hills and the valleys in this area, are made up of material deposited by glaciers. And when you see the end of this glacier, the end of our glacier here, and you see all the boulders embedded in the ice, you realize just how much material a glacier can carry along. Also, although it was about -20, in this little sort of sheltered place, already melting has begun. Now, real melting only occurs here sort of in July and August, but you can see from the snow and from the dripping water that in the middle of the day, when the sun is at its highest, melting is already beginning on this particular glacier at the bottom end of it. And what we've really done here is gone from the pit in the snow at the very top of the glacier, where we were measuring the snow coming in, to the very end of the glacier, where most of the melting will occur, and where later in the summer we will have to measure the melt as it occurs. In at least one of these shots, you can see there's kind of a cave leading in under the glacier, and that's where the previous summer water came flowing out, and it sort of melted out a hollow in there, and you could walk into that cave, although later on it would get very dangerous because boulders would fall. In a sense, you're going under the soul of the glacier, and there's a good shot with some icicles and some melting snow, and you're looking in literally at the bottom of a glacier in that particular location. Now again, 11,000 years ago, there was ice here in Peterborough, more than a kilometre thick, just like that, and most of our landscape, that's where it came from. Then there's a sequence of us drilling. There's a tall pole, an aluminum pole, and we're drilling with the snowmobile alongside us and other aluminum poles on the snowmobile. And although it's still snow covered here, this is the bottom end of the glacier. Quite soon the snow will disappear and melting will start at this location. And that pole that's behind us, that gives you an idea of how much ice melted the previous year, because we drilled that pole all the way in. In fact, we drilled a hole that was so deep that we dropped the aluminum pole into it, and you had to reach down with a tape to measure how far down it was. So we know that amount. So that's how much melted at this location last year. Now that amount was partly replaced by snow coming in at the top of the glacier, but in fact, the previous year and the year we were here, this glacier, more ice melted than it gained, and that's been true for the last 10 years. And even over the last 30 years, this glacier has retreated probably 200 meters, which means that it's got much thinner and much smaller in that period of time, which suggests that the world's climate is warming up. The drill we use it looks a bit like an ice fishing drill, and in fact here in Peterborough we use similar drills to that on the lakes, as do people who fish through the ice. But in fact it's a finish drill which has a special bit to it, and we use it to drill perhaps 4 meters down, which is a long way. It's hard work, but it's better for us to use a hand drill like that than to bring up a heavy power drill and then find that the power drill won't work. And particularly as it's difficult for us to get the snowmobile onto the glacier, it's not easy for us to carry additional weight. But you can see from the pole behind us just how far down we have to drill each year to measure ice melt. And then there's a clip back to our sleeping house. You see the skis, you see the small generator which we use for power and that kind of thing. The hut has been there for many years. It was one of the first fiberglass insulated houses, and it's a tongue and groove, very simple construction, and it's strapped together by metal straps. And there's some shots of the interior which gives you an idea of how we work. There's a sleeping part at the back. Some people have trouble sleeping there because of the light, and although we have curtains in the back, I never have, and Miles Ecclestone never has, but some people do. To me, I can always tell when it's night time because of the chill in the air. Even though the sun is up, it's not as warm, and that seems to have the same effect on me psychologically as the darkness, and I just feel sleepy and I go to sleep.
This is where we sleep. Rustic home.
Okay, charging time.
Bunk beds. More bunk beds. You can sleep 8 comfortably here. Just your skis. Map. How's that for a view? Pretty nice.
We are on Colour Lake. Difficult to imagine the lake is there. The ice is perhaps 2 to 3 meters thick on the lake. It is, of course, our only source of drinking water apart from melting snow, which is a very tedious business. And so what we're doing here is we're drilling a hole in the lake with a view, hopefully, to getting a block out so we can analyze it eventually. Also measuring temperatures in the lake and measuring the chemistry of the lake to see what has happened to it during the winter. This lake is very unusual because it is naturally acid. it has an acidity which is a bit like a mild vinegar, even though it's in an area which includes limestone, which normally would buffer the lake against acidity. And it's acid because of chemical processes at the bottom of the lake, not because of acid rain that we're all familiar with, but because of processes actually going on in the lake itself. And it's been acid probably for 7,000 or 8,000 years. So it's interesting because it gives us an example of what lakes around here, for example, might be like if they do become acid as a result of acid precipitation. And what happens is that animal life in the lake is killed off. The lake becomes very, very clear, so you can see to great depths in it. Vegetation, thin vegetation, weeds and so on, grow to great depths because vegetation needs light. The light can get to great depths in these clear lakes. So essentially an acid lake is like a swimming pool. It's perfectly clear. It's been treated with something which has killed off animal life in it, and down the sides of it, almost like the sides of a pool table, you can see green when there's no ice on it, that is, as there is in this case. So what we're doing here is we're drilling a hole to start sampling the lake and ultimately to get a sample of the ice, and to follow this process of what happens in a lake which is completely acid. And in this drilling, you'll see that we drill 3 holes with the auger, and then with the saw, we cut between those holes to free up the block in the middle, because we need the block to sample it. So it's a quick way of getting the block.
Cutting the ice block.
The saw, which you see, which is used to cut out the block, we bought at McKay's Surplus, which is just north of Lakefield. And I recommend McKay's Surplus to anybody in this area. When we went there, we said we needed a crosscut saw with a handle on only one end. And he said, well, what do you need it for? And I explained that we needed it to cut blocks of ice. And he said, oh, you mean an ice saw? And he had actual ice saws that were left over from the time when people used to cut blocks of ice for the ice block industry here in Peterborough. Then there's a sequence with the block loose and looking down in the very, very clear acid, as I mentioned, water. And you can see the layers of the ice and so on when we've taken the ice block out. And there's a sequence there at the end. We had taken the ice block out, but in fact a piece had got trapped in the bottom. And fortunately for us, we were able to get it, and so we had the full thickness of ice which we could use for our chemical analyses, and then we can use the hole for making measurements of the water. The lake is 25 meters deep, and we do measurements of temperature and conductivity and do various chemical analyses of the water.
No need for an ice cube tray up here.
No. Well, as the lake ice forms, the natural dissolved chemicals in the lake water are exhaled out of the ice and into the lake. And the rate of the loss of ions is dependent upon the temperature. So as we section up the ice core and we analyze the total dissolved chemicals in each of these bands of ice that we're cutting up, we should see a relationship between the temperatures occurring through the winter and the concentration of dissolved chemicals in each of these layers. And the faster the ice forms, the higher the concentration of dissolved chemicals there should be in each of these layers. And the slower it forms, in other words at warmer temperatures, we should see a more efficient exsolving or loss of the dissolved chemicals out of the water as the ice is formed. So we should see a difference in dissolved chemicals as we go from the top to the very bottom. And we're going to relate this to the record of temperatures that's been kept here all winter by a group from the University of Nevada.
Let's go over here first. We know this what this other guy's doing. Oh, here's Alex. What are you up to, Alex?
Well, I was just about to download some of the data from the data logger. It's recording down at the, by the
Oh,
lower
yeah. We stopped and saw that. It's still logging fine, thank you.
You have to do quite complicated analyses in rather difficult conditions, but nowadays with portable computers we can do much more than we used. Some samples we simply collect and accumulate, keep them frozen or keep them cold and stable, and bring them back, and they're analyzed in the south. It's getting to the point now, we aren't there yet, where you can do a lot of this work and then transmit it immediately by satellite with quite small equipment, and it's analyzed back at the university. It's called the Crusoe Glacier, and you can get an idea from the size of the figures what the end of this particular glacier is like. This is as far as this glacier gets. It doesn't reach the sea, but you can see pieces break off it and they will ultimately melt. It's not as big as the glaciers that we work on, but you can see by any other standard it's a very big glacier. It's called Crusoe Glacier after Robinson Crusoe. When I was working on this island as a student, there were only two of us there, my supervisor and myself, and we went away from a camp for 10 days, leaving most of our equipment there and just taking with us the stuff we could carry. And when we came back, we found two wolves had destroyed the camp completely. They had torn the tent up. They had chewed open cans of butter and cans of corned beef and sacks of sugar and that kind of thing. They are dogs, of course, so what they hadn't eaten they'd urinated on. And so we had to build a shelter out of drums and what was left of the torn canvas. And my supervisor, who was a bit romantic, said it reminded him of Robinson Crusoe, so we called this glacier the Crusoe Glacier. There are good shots here of the end of a glacier. Again, you can see how dark the material is, and glaciers carry a lot more than you think. They are rivers. Let's say a river, say it's 400 meters thick, and this one 1 kilometer wide, and throughout it there are rocks and debris which it's carrying. And when the glacier melts, all that stuff comes out. And again, that is the material of which the Peterborough landscape is made up. 11,000 years ago, ice, much, much thicker than that, was here. When it melted, it left behind everything it was carrying and formed all the hills and valleys that we live in. There's a sequence then, after the snout of the glacier is gone, of a dark, muddy looking stream, and it's another set of these sulfur springs, which run all winter long because they're so salty. Although they're running, they're very, very cold. The water in them is well below the freezing point, and what you see there is mud and deposits of salt-like material which has come out of the water. The baby glacier in the background, which is the triangular-shaped glacier very high up, that we also measure each year. To the left of it, there's a dry valley which is called the Trent Valley after Trent University, and then the Crusoe Glacier, which is a long way away from us and well above us. You can see it there, and later on there are some shots of us working on that glacier. There is an advantage to measuring glaciers of different sizes. A small glacier will respond very quickly to climate change within a few years, whereas a very large glacier might take hundreds of years before it will reflect the change. So the small glacier we work on is more likely to show what the climate is doing now, whereas our large glacier is much better for showing what it's doing over, say, the last 10 or 15 years. This is a piece of ice which is broken off a glacier and floated out to sea and become frozen in the sea ice. So we are walking on sea ice which is frozen that year in the Fiord, and behind it there's a great big piece of glacier ice. Now, I don't know which glacier that iceberg came from, but it could have come from 100 or 200 kilometers inland, come all the way down from the mountains, down into the sea, broken off the glacier, and then floated away as an iceberg, and has become trapped in this particular location. You can see the ice is the same type of ice as we saw at the front of some of our glaciers.
Well, here we are getting ready to go up Wolf Mountain over to Baby Glacier. Now we're going to walk over to that bare spot right there. We'll skidoo over. We'll walk up this hill here, that bare spot, and then cut up the ridge. Okay, Miles. About there. contour line. Well, there we are. You can see base camp. We skidooed around here. And you can see the track coming up. And we came up this hill, which you really don't get a feel for, so I'm just going to span around here.
Okay, this is the way, guys. Just follow me. We'll follow this caribou track. It like knows where it's going. I must say this caribou looks like a mouse.
The caribou that's just like the salmon. It wants to...
The baby glacier, folks. A hardy, plucky band of geographers. Adams and English up top still. Following the rule, always stick to the high ground, which doesn't really pay off when you can walk a contour line around and save yourself coming down this slope, which is very slippery, and onto the baby glacier.
It's a small glacier, but it's very steep, and particularly when the snow has gone, one of the problems is walking on it, because you have to go down to the end of it, and then you need crampons on your feet, which are spikes that you put on your boots. And there's a pan across it, and then there's a location where we put a camp.
Cryoconite, or cryokyanite surface.
Yeah, look at that.
There are some shots of some very compact snow in my hand, and it's shown because in order to tell where this winter's snow cover finishes, you go down to where the remains of last summer's melt are, and that's what that shows. So we've just come back from up there, folks, and now we're going to go into the kitchen house. See who's here.
Come in, Miles.
Oh, there's someone there.
Just a cup of tea.
Cup of tea, yeah.
Mhm.
Look at all this stuff here. Holy.
Yep. All sorts of exciting things here.
Oh, yeah.
This is our little stove. We put a folding oven on it for cooking pizza and stuff like that.
Oh, all the comforts of home.
And then look at all this food we got.
Oh.
It's incredible. Shelves and shelves of it.
Oh, gee, I see some...
Some of that stuff's for eating here, and some of it's for taking up on the glacier or taking out to fly camps, you know, that kind of thing. Yeah, you can see we got all sorts of products there. I noticed some Quaker Oats and some Aunt Jemima. A few other bits and pieces. No, I must say, we eat much better than we used to do, Miles.
Well, you were telling me that the other day, Pete. I don't know whether to believe you or not. I mean,
Well, in the good old days, it used to be bread and water, and the water if we were lucky. Okay?
Yep. I don't know, it's co-pilot. This is the crew that will stay on. We're there for another couple of weeks, but then after that they stay on and do work measuring the melt of the ice in the lake, water coming into it, and so on. They include students from Wilfrid Laurier University in Waterloo and from Trent. One of them, Peter Doran from Trent, is now working in the Antarctic, in fact at a Russian base. Increasingly now, there are both male and female students working in the north, and from Trent in particular, a considerable number of women students has in fact worked in Axel Heiberg and on our other projects in Labrador. Then we see the plane taking off, and it's going back to Resolute, and that's our last contact with Resolute for some time. You get an idea of how crowded our kitchen house is when everybody arrives, and you'll see us all sitting around the table, and it's pretty cramped, and you can well imagine if you're staying there for weeks, you have to really be quite careful that your relationships are good and healthy. And in fact, we would generally work in different parties, and some would go away and work, for example, on one of the glaciers and stay in a tent for a few days and then come back, so that people get on each other's nerves as little as possible. It's a good group of students you see there. There are professors from Wilfrid Laurier and Trent. There are some master's students and some third and fourth year students from both universities, which gives you a great mixture. What we try and do at Trent is not only do good scientific work there, but use it to train our students. And it's this sort of a setting which helps us do that. This is us going over to the White Glacier where we had been before and showing the new group of students how we do the drilling, showing them where the stakes are located for the measurements and that kind of thing. These are tiny birds which migrate enormous distances, and this pair that are in these shots must have just arrived in Axel Heiberg. The ground is becoming bare and the snow buntings arrive, and they have come from mainland Canada thousands of kilometers to the south. And then there are some shots of the end of the glacier and showing just how much material has come out of one of them. And then there's a pan down the Expedition River Valley. In the end, by the end of the summer, that valley will become a river. And an old snowmobile, two old snowmobiles that are left from working groups some years ago. It's a week or 10 days after the students arrived, and they decided to have an Axel Heiberg Games, and so they've invented a series of sports, and one of them is throwing the concretion. There's a thing there that looks like a cannonball, and in fact it's a special rock formation that occurs in that area, and you can get lots of these cannonballs there, and the students have one, and they're seeing who can throw it the furthest. And then later on in this sequence there are other of these games. This sort of thing is very, very good for a group like this. People work very hard. They tend not to sleep enough because some people don't adjust to the 24 hours light. So this kind of thing is very useful. And now, it's my privilege to present the Mueller Memorial Tray. It's actually the Mueller Memorial Melt Tray from the accumulation zone of the White Glacier Axel Heiberg. This has spent more than one winter on the glacier. You can observe how the glacier has slightly deformed it. Okay, and I'd like to present this, if he would come forward, to the captain of Team Click, who win the gold medal.
Give it to
Let's hear it.
Very nice.
What can I say?
Hold it up so we can all see his name.
Sport.
Friday, May 24th, helicopters arrived.
Helicopters are very expensive, and it takes a long time for a helicopter to reach us where we are there. And so when they arrive, we have to make all possible use of them we can. And in this case, we're mainly using the helicopter to take a camp. That's a camp which will be located all summer on the Baby Glacier, which is the triangular glacier up by the mountain peak. And in the first part, we're being briefed on helicopter safety, which you always are before you use helicopters. And then we load up the helicopter, we fasten things to its struts, and it goes up. As you can see, the cloud is very low. This pilot came in a very circuitous route. He kept at sea level, kept on the sea, went round the island, and came up the Fiord to where we were. And with our equipment, he had to fly, in fact, into a cloud. So he flew up, he went into this cloud, we unloaded it, he left some of us there, and then he flew out of the cloud to pick up more people, and then go to do some more work before he could return to his base. These helicopter pilots are, in my experience, quite different from the fixed wing pilot. They are almost fanatics about their machines. They almost invariably, the pilot is an engineer. He'll often have an engineer with him as well, but he knows everything about his machine. Whereas with the fixed wing aircraft, you quite often have pilots who are knowledgeable about their aircraft, but they couldn't take it to pieces and put it back together again. whereas helicopter pilots, it seems to me, have to be able to do that. They depend so much on their machine. So the net is picked up, and in the background you can see the cloud, and in that cloud is a mountain. Behind the mountain is the baby glacier, and that's where our camp is going to be located for the rest of the summer. Now he can get up there in a few minutes. It would take us 3 or 4 hours of steady climbing without a pack to get to the same location. So he sweeps in and he'd come back for more loads. And what they're doing here, they have a Nansen sled, the toboggan you see there, and they have got a drill system which goes all the way to the bottom of the lake, and they're trying to drive a drill at the bottom into the lake to sample the sediments in the bottom of the lake. It's a long, arduous process. I'm not sure how deep the lake is there, but it might well be 10 meters down of water, and then they're into the sediments. So that's what they're doing. Now from the sediments, you can get information about what has happened to that lake over hundreds or thousands of years. You can analyze each layer, and you can see what the vegetation was like. You can get some idea if it was cold or if it was warm, and that kind of thing. Moment. And then there's a sequence of trying to get water samples from the lake, and you see that Julia Boike has a plastic tube, and they're trying to get water through it in various ways. You don't normally do it in the way they're doing it. You have a pump, and we often try and get samples of water from all levels in the lake, starting at the very, very bottom, then come up so many meters, take another one, come up so many meters, take another one, so we get an idea what the water is like throughout the lake. Normally what happens in the winter is all the gases and dissolved solid material which is in the water, which froze to form the ice cover, is pushed out as the water freezes, and so is concentrated immediately below the ice. The same thing happens in an ice cube. When the water freezes in an ice cube, any impurities that are in it are pushed to the edge of the ice cube. So in this case we've got 2 or 3 meters of ice, and all that material has been pushed into the layer of water immediately below the ice. So it's very, very concentrated. And the bottom of the lake, which is next to the sediments, also has quite high concentrations, and then it's less concentrated in between. There is some melting going on now, and it's still below freezing point, but the sun is out, although it's not very high in the sky, for 24 hours every day, and gradually on south-facing slopes that gets rid of the snow, and you start seeing mud, and things start to grow, and you start seeing little birds. Again, in here I see some of the snow buntings which have arrived already from the south, and these are some more shots of the sort of salt springs that we saw in some earlier shots, and now they're becoming more open. Now this is very saline water which runs all year round, but now the ice around them is beginning to melt. And one of the shots shows some very fine frost, like hoarfrost, on some plants, and that has come from the moisture that's come out of these springs, which are running even though it's still very cold. And one of the shots shows that already there's quite a pool, which is very, very cold. The water is well below freezing, of these sulfur springs, and the ice on the top, that you see I'm standing on, that is the ice which is formed during the winter on top of these springs as they were flowing. And the close-ups show the springs running still from the little holes they appear from out of the mountain. And some of the other shots show the very cold water and the salt-like material deposited around the springs. And you see a variety of crystals, which is where, again, like vapor, rises from these very, very cold pools and is deposited to form those really nice crystals. And then we take off again in the plane, and this is when we leave, and we leave the students behind for the rest of the summer. Goodbye.